And right now we're going to go over to Santiago Gimeno, who will be kicking off the conference. So please welcome Santiago Gimeno. Santiago is a software engineer at NodeSource and a contributor to the Libuv and Node.js projects. Here he is with Uncovering Libuv's Secrets, a Practical Approach. Over to you, Santiago.
Hello everyone, I'm Santiago Gimeno, engineer at NodeSource and contributor to the Libuv and Node.js projects. My main objective with this talk is going through parts of the internals in Libuv while showing you some of the work I've been doing to try to add a new backend for Linux based on the new IOring API. I divided the talk in 4 parts. On the first part, I'll go quickly through some Libuv basics. Next, I'll make an introduction on what IOring is. Then I'll show how I've managed to integrate it into Libuv. And finally, I'll show some results at what the next steps might be. So, what's Libuv? As it's widely known, it's a cross-platform support library with a focus on asynchronous input-output. It provides abstractions for network support, timers, file system access, DNS support, and some other functionality. It was originally designed for Node.js, but it's also used by other projects such as Julia, Lubit, CMake, and Bind. With regards to the Libuv architecture, everything revolves around its 7-loop implementation, which is tied to a single thread. At this point, I'd like to introduce the event provider definition, which is an OS mechanism used to post execution of the event loop and wait for an event it has been previously registered in the provider. Libuv uses different event providers in order to track input-output activity depending on the underlying operating system. Epoll for Linux, kqueue for macOS and the BSDs, event pulse for the Solaris, IOCP for Windows, and poll for other Unix flavors. Some operations such as file system access haven't real asynchronous support from the operating system, so they're executed in a separate thread pool. In the following graphic, we can see the different stages in which the Libuv event loop implementation is divided. We'll first check whether the loop is alive or not, which basically means if there are any active handles or requests. If not, it will gracefully exit. Otherwise, we'll start a new loop iteration. In the first stage, we'll check if there are timers to be fired and call its callback if so. Then we'll run the pending callbacks, which are specific callbacks for tasks or requests already finished that need to be called in the next iteration of the loop. Then we will go to the idle and prepare handle callbacks, if any. In the input-output phase, we check for the event provider tracking activity, and this could be either, for example, incoming connections to be accepted, incoming data to be read, etc. Then we'll call any check handle callbacks if any was set, and finally we'll call the close callbacks. Anyway, if you want to check how this is really implemented, I have added a link to the implementation of the uvrun method for the Linuxes, which is very easy to follow and will probably make the things clear. And finally, a brief explanation on how Libuv tracks input-output, which is going to come handy later in the talk. There's the UVIOT struct, which represents every input-output resource Libuv is tracking. And one other thing is it stores the input-output callback and the file descriptor of the resource. We'll call elements of this type watchers from now on. Then we have the UVIO start and stop method, which add or remove the monitor events on a specific resource. And finally, in the UVIO poll method, the resources are added to the specific event provider for tracking, and also events are retrieved in case already triggered. Moving on now to the IOring section. So, what's this IOring API? It's a new asynchronous API for Linux introduced in kernel version 5.1 and created by Facebook engineer James Axwell. Its name comes from the use of shared ring buffers for user-space kernel communication. The use of these buffers allows to reduce the number of syscalls needed. It also provides some other functionality that may increase the performance even more. But how does it really work? As mentioned before, there are two ring buffers for the user space kernel communication. First is the submission queue, SQ, that is used to submit requests from user space to kernel. And second, you have the completion queue, CQ, to receive the completion of the submitted request from kernel to user space. The requests for async operations are inserted at the tail of the submission queue, one entry SQE per operation. Then these requests can be submitted to the kernel from where they're consumed from the head of the submission queue. These requests can be batched, as we'll see later, which will allow us to save some syscall. Finally, once the kernel has processed the requests are inserted at the tail of the completion queue, where they can be retrieved from user space. One CQ event, CQE for SQE. The IO ring interface consists of only 3 syscalls. The IO ring setup, we set up both the submission and the completion queues and returns the IO ring file descriptor, which will be used to run subsequent operations on the ring. The IO ring enter, which allows to initiate and complete operations. A single call can both submit and wait for completion. There are a lot of support operations to perform the same functionality as other syscalls already do. Examples include write B, read B, connect, accept, send message, etc. And finally, the IO ring register syscall that is used to register buffers and file descriptors in the kernel, so the kernel can reference them, reducing input-output overhead. But using the syscalls directly on real code is not that simple. For example, in order to set up an IO ring instance, additional mmap calls are needed. So Libuv ring is provided to make our life easier, though for most complex cases, the syscalls can still be used there. So now I'm going to show you a very basic example of using IO ring, in which we'll create a socket pair. Then we'll send data from one end to the other, and then we'll close the connection. Notice that the IO ring syscalls are not used directly, but the Libuv ring methods are. So in the first section of the code, a pair of connected sockets are created with the socket pair syscall. Then we'll set up the async rec struct with all the operations we are going to perform in this example. In our case, it will be reading from both sockets and writing to the first one. Finally, we will set up the IO ring instance by calling the IO ring queue method, which is a wrapper over the IO ring setup syscall. And in this case, we will set up the submission queue size to 16 elements. Next, I'm going to present how we will be performing the async read and write operations. The idea is going to be always the same. We will first set up the operation in an SQE element, and then we will submit it. Having that in mind, what we do is we first prepare both read operations on both sockets, and then we prepare the write operation on the first socket. A couple of helper functions, do read and do write, have been created, which basically do the same. So first, we will retrieve an empty SQ element from the submission queue by using the IO ring get SQE method. Then we'll fill the element with the operation we want to submit, whether it's a read or a write. Notice that the arguments set for the SQE are exactly the same as the read via and write via syscalls. And finally, we set the user data field with the async read pointer, which will be passed to the completion element CQE and will allow us to link both the completion with the submission. Then, after creating the 3 requests, we will submit them by using the IO ring submit method, which wraps the IO ring enter syscall. Notice that in order to submit 3 requests, in this case, we only use 1 syscall. And finally, we'll see how to wait and retrieve completion events, CQEs, from the completion queue. What data is stored in those CQEs and how to deal with that. So here's the main loop of the program. It will wait for completions using the IO ring wait CQE function. And when one is available, we retrieve the user data field and cast it to the async request pointer. This pointer has been propagated from the submission request that caused this completion. We then check whether it's a read or a write operation. I'm going to focus only, in this case, on the read completions. So first, in the second socket, we'll retrieve the first completion because we will be receiving data. In the secure rest field, we will receive the number of bytes we have read, and then we can close the connection. And then I close the connection. So the second completion will be on the other socket, which will detect that the connection has been closed. Notice that secure rest is 0, and then we close the socket as well. Notice that after handling every completion, the CQ elements have to be marked as free, so they can be reused by the kernel. For that, we use the IORing CQE sync method. So wrapping up the IORing section, these are the main benefits IORing provides. It's a completely async and homogeneous API, even for file system operations, so there's no need to use a separate thread pool. Cheaper syscalls because we just use a bunch of IORing enter syscalls that need less data copied between user space and the kernel. We can use fewer syscall. As we saw, we can batch multiple requests in only one IORing enter syscall. There's even a special mode called submission queue polling, in which the kernel grabs requests directly from the submission queue, avoiding even more IORing enter syscalls. The problem with this mode at this moment is that, as far as I know, you need to run your program as a super user to use it. I think this restriction will be dropped starting probably in 5.10 or 5.11. And finally, there's some gains you can have by using the registering buffers or files functionality. After this long introduction, let's go to the gist of the talk. How can we integrate this into Libuv? I thought of two valid approaches. The first approach would be keep using epoll as the backend provider, but use IORing for selected operations. This is possible because the ring file descriptor is pullable. There's already a fantastic pull request by Zach Bjornsson, which shows relevant performance gains by executing file system operations by using the IORing API, and it avoids using the thread. It's a less intrusive approach, which makes it easier to integrate. The second approach, which is what I've been trying to accomplish, is replacing epoll with IORing as the event provider. It's more intrusive as a new full IORing backend is needed. The main problem I face is that migrating from the current syscalls to IORing operation is not easy, especially when trying to keep the ABI compatibility. For example, typically a read syscall would return the data in line. On the other hand, with IORing, that is not always going to be possible. So we are going to need to add some kind of a state to the Libuv handle or request to deal with that. Doing it while keeping ABI compatibility is not straightforward. So as a first step, I set this problem and just use the poll add and poll remove IORing operations that are akin to the epoll CTL ops and see how it would go. But first, I like to give a brief reminder on how epoll is used on Libuv. So epoll create one is used in platform loopinit method in order to create the epoll instance. Then the epoll CTL method is used to add, remove, or modify file descriptor to be observed by the epoll instance. It's called whenever a watcher is added or removed from the loop. For example, in the UV poll method, the file descriptors from the watchers are added or modified to track specific events. Finally, epoll wait is used to wait for events or return in case of timeout. The timeout argument is important as we depend on it, among other things, for the timer implementation to work. It can be used in the following ways. If timeout is stopped, epoll wait will return immediately. This is used in Libuv in different cases. For example, if there are not active or active requests of active handles, or if there are any handles, idle handles set up, or if there are any pending or closing handles. Otherwise, for example, if there are no timers, we will set up the timeout to -1. In this case, epoll wait will wait indefinitely until there is an event. And finally, if the timeout is greater than 0, it will return either on an event happening or if the timeout is due. It is used in the UBI-IOPOL method to return events from the provider. In the case there are events, we can from the events we can extract the watcher and finally call the watcher callback with the events received. So now, what have been the main modification I had to do to implement the IO-ring backend? First, I had to expand the UBI-loop-T struct to hold the IO-ring structures. So we define an IO-ring data struct that holds the Libuv IO-ring structure, and we add a pointer to this struct in the loop struct, replacing an unused pointer to maintain ABI compatibility. I've also added a helper method to retrieve this field easily. Also, new methods for the loop initialization release have been implemented. So we have in the platform loop init, the IO-ring data struct is allocated, and the IO-ring instance is set up with a submission queue size of 4096, which is the maximum allowed by the IO-ring API. On the platform loop delete function, with the IO-ring instance is destroyed and removed from the loop. Finally, a new UBI-IOPOL implementation is also needed. In order to track watchers activity, we'll go through the loop watcher queue and basically perform the same dance we use in the previous example I showed you. We'll first retrieve the empty SQEs from the submission queue. We fill them with the IO-ring of pollad operation, and in the user data field, we'll insert a pointer to the watcher, so it's propagated to the completion event. Finally, all the field SQEs will be submitted at once. Next, we'll wait for completions or timeouts in a similar way as we did with epoll wait. For this, we're going to use the IO-ring wait CQE's Libuv method, which accepts 5 arguments, the important ones being the third, which defines the number of completions before returning, and the fourth, that gives us the possibility of registering a IO-ring of timeout operation. This timeout operation works in the following way. You pass as arguments the actual timeout value as a timestamp and the number of completions to wait for. So the operation will complete when either the number of completions have occurred or when the timeout is due. In the first case, it will return 0. In the latter, it will return e-time. This way, we can have the same functionality that epoll provided. If timeout equals -1, the number of waits will be 1 and the timestamp will be 0. So the method will wait indefinitely until a new completion happens. If timeout equals 0, the number of waits will be 0 and the timestamp will be 0. So it will return immediately whether there are completions or not. Otherwise, if timeout is greater than 0, the number of waits will be 1 and the timestamp will be 0. Will be actually set to the actual timeout, and the function will return on either new completions or when the timeout is due. And then finally, we retrieve the completions and call the watcher callbacks. For this, we use the IO-ring for each CQE helper, which allows us to loop through the current CQE events available in the completion queue. First, we check if user data is set to Libuv UData timeout, which we just ignore because it's the completion of the timeout we had set in the IO-ring method. Otherwise, we know it's an event for the watcher, so we cast it into the UBI-IOT struct. Then we get the events returned from the rest field, this is important. We have to arm the watcher again, as the IO ring or poll operation works as epoll one shot. And finally, we call the watcher callback. Then finally, we mark all the retreat CQEs as free with the IO ring CQE advanced method, which does exactly the same as the IO ring CQE sim method we had used before, but for multiple CQE entries. So now I'm going to show you the results of my work. So after applying these changes, here are the results. Basically, the libuv test suite passes. The libuv benchmark results are quite on par with the poll ones, which is probably to be expected because what you may win in syscall optimization, you lose it when you have to send the poll ad operation after it's complete. But there are some good news I'll show you in a moment. So for the moment, right now, here's a link to a branch where you can play with that code. With regards to the next steps, I like to integrate this work on top of the other pull requests I talk about that implemented the file system operation. Then I like to add as many operations as the IO ring API provides. The main issue being, as I already mentioned, keeping API compatibility. So maybe targeting version 2 is good for the moment to see if it's worth at all. And finally, the good news, I already have a branch adding support for the send message and message IO ring operation for UDP handles. And though it's still a work in progress, the results are really promising, especially once the load starts to increase. I include also the GitHub branch, so you can play with that. And now let me show you the actual results. So I'm going to, in the following charts, we're going to see the results of the UDP PAML libuv benchmarks with 1 UDP senders, 10 senders, 100 senders, and 1,000 senders. The x-axis represents the number of receivers. That means UDP handles receiving traffic. And the y-axis, the number of messages per second. Blue for the IO ring backend and red for the epoll backend. So we can see that with only one sender, both IO ring and epoll perform more or less the same. Maybe IO ring a bit better, but nothing significant. But as we increase the number of senders, IO rings start to perform much better. So in this case, with 10 senders, we can see a performance increase of about 35%. While with 100 senders, the increase is close to 70% better. And with 1,000 senders, the performance increase goes above 100%. Also notice that with the epoll implementation doesn't seem to keep up with so much load. As we can see that the performance is worse than we had with 100 sender, while the IO ring seems to do just fine. So as I said, even though this is still a work in progress, it looks very promising, and I'm really looking forward to keep working on it and even add support for other handlers, such as the streaming ones. So that's it from me. I hope you found the talk interesting, and thank you everyone.